Hello. In this video we're going to cover special relativity. This is the theory put forward by Einstein to explain the apparent contradiction between the results of the Michelson-Morley experiment and Galilean relativity. By the end of this lesson, students should be able to state the meaning of an inertial frame and recall Einstein's two postulates. Students should understand the meaning of time dilation and should be able to use the time dilation formula. In the last lesson, we discussed the idea that there is no absolute motion. Instead, an observer moving at a constant speed will feel the exact same laws of physics as an observer who is stationary. Another way of expressing this is that an observer moving at a constant speed has no experiment that they can perform to prove that they are moving. In Einstein's formulation, we say that an observer travelling at a constant speed is travelling in an inertial frame. Einstein used this idea to formulate his theory of special relativity. He took two postulates. The first is that the physical laws have the same form in all inertial frames. That is, whatever inertial frame we use will get the exact same experimental results. The second is that the speed of light is invariant. That is, if we move away from a source of light or towards a source of light, we should measure the same speed, c. Einstein took these two postulates and applied it to a simple thought experiment. An observer on a train uses a light clock. The light clock sends a pulse of light from point A to a mirror B, which then reflects the light back to point A. From the perspective of the observer on board the train, the light has taken a time delta t to travel between these 2 points. This is equivalent to 2 times the length L divided by the speed of light c. We call this time period the proper time. The proper time is the time measured by an observer who is stationary relative to events, in this case on board the train. However, to an observer on the platform things look different. An observer on the platform will see the light travelling a distance d, and hence will take a time 2d divided by the speed of light c. These two time periods are clearly different. We have the proper time, t, measured by an observer on the train, and the time t dash, measured by an observer on the platform. Einstein's leap was to realise that these two times are different. An observer on board the train will record a different time relative to an observer on the platform. We start the derivation by using Pythagorean theorem to derive the time dilation formula. However, as a full derivation is not required for the exam, I will leave this as an exercise for the keen viewer. Don't be concerned if you didn't follow the derivation, as what's important to you is that you know how to use the time dilation formula for the exam. However, as an additional point of interest, I'll simply point out that the factor 1 over root 1 minus v over c squared is sometimes known as the Lorentz factor or the gamma factor. What is important for the exam is you understand the meaning of the time dilation formula and can apply it mathematically. The time dilation formula is again best understood in the context of a thought experiment. Imagine you have a twin. While you stay on Earth, your twin gets on a rocket ship and travels very fast off into space. If your twin then returns after a very long time, you will have grown old while your twin would still be relatively young. While your watch has been moving much faster, your twin's watch has been moving relatively slow. This may be best illustrated through using the formula. Let's imagine your twin moves at speed 0.1 c, or 10% the speed of light. Putting this number into the equation, you should see that the time you measure t dash will be 0.5% faster than the time measured by your twin, t. However, let's see what happens when your twin now moves at 0.99 c. The time which elapses for you should now be 700% faster, or 7 times faster than that which has elapsed for your twin. One place where this has been experimentally measured is muons moving towards the ground from the upper atmosphere where they are created. In a lab, muons have a half-life of less than 2 microseconds. Owing to this short half-life, most muons should decay before they reach the ground. However, at the ground, we do detect a significant proportion of the muons, a significantly higher portion than we might expect. The reason for this inconsistency is that muons travel incredibly fast, meaning in their inertial frame, time moves relatively slow. This means that although the muon should decay in microseconds in the inertial frame of the observer, in the inertial frame of the muon, far less time has elapsed. There are many good links to this in the video, and I'll also share those links in the comments. In the next video, we'll discuss length contraction and Bertozzi's experiment, which will bring us to the end of the turning point section of the course.